Before the first second, there was nothing. No clocks, no stars, no history. Just an absolute void. This audiobook takes you to that impossible moment, the birth of time. How can something arise if there was no before? What forces shaped the first heartbeat of the universe? A serene journey through one of the greatest enigmas of cosmology, the moment when everything we know began, even time itself. Imagine that time, as we know it, did not always exist. How can this be possible? Science shows us that time as a dimension was born along with the universe in a cataclysmic event known as the Big Bang. However, this event raises more questions than answers. If time began at that instant, how can we talk about what happened before? Is it possible that there was a before time? These questions lead us to reflect on the very nature of reality. As we explore the beginning of time, we encounter complex concepts that challenge our intuition. For example, the idea that the universe began in a state of high organization seems to contradict what we know about entropy. How is it possible that everything we know today, with its chaos and disorder, emerged from such an ordered state? This enigma invites us to reconsider our notions of time and matter. Moreover, have you ever imagined a time that does not flow linearly? Quantum theories suggest that in the early moments of creation, time may have been discontinuous or even fluctuating. This challenges our perceptions and leads us to wonder, could it be that time, as we understand it, is merely a construct of our minds? As we delve into this fascinating journey, we also encounter quantum gravity, a theory that seeks to unite the laws of quantum mechanics and gravity. How did this union influence the birth of time? Reflecting on this, we face the complexity of the cosmos, where each discovery reveals more mysteries. Cosmic inflation, a moment of dizzying expansion just after the Big Bang, adds another layer of wonder to our understanding of time. What happened in those critical moments that laid the foundation for everything we know today? The questions are endless, and often the answers lead us to new uncertainties. Creation from nothing is perhaps one of the greatest paradoxes we face. How could time arise if nothing existed before its beginning? This question confronts us with philosophical dilemmas that have been debated throughout history. The arrow of time, which points us in one direction, also puzzles us. Why does time move forward and not backward? In this exploration of the beginning of time, each mystery we unravel leads us to even deeper ones. From the initial singularity to Stephen Hawking's theories of imaginary time, each concept invites us to question our most fundamental beliefs about existence. Are we ultimately trapped in a labyrinth of time and space, or is there a way out towards a deeper understanding? The future of time also poses intriguing possibilities. Some scientists suggest that just as it had a beginning, time could have an end. What would this mean for us and for the universe as a whole? Thus, as we immerse ourselves in these mysteries, we not only seek answers, but also explore our own nature and the role we play in the grand scheme of the cosmos. Each question opens new doors to understanding, and each answer challenges us to think beyond the limits of our perception. In this journey, let us remember that the beginning of time is a reflection of our infinite curiosity and our desire to comprehend the unknown. In the fascinating universe that surrounds us, one of the most intriguing questions we can ask ourselves is, why did the universe begin in such an ordered state? It seems contradictory, doesn't it? In a world that, as it progresses, tends to move toward disorder, the fact that the universe was born with such a high level of order raises a curious paradox. This low entropy paradox leads us to rethink our understanding of time and the very nature of the cosmos. Entropy is a concept related to the disorder of a system. In simple terms, the second law of thermodynamics states that the entropy of a closed system always increases over time. However, the universe, at its birth, was extremely ordered. How is it possible that an evolving cosmos, where disorder is the norm, began in such a perfect state? To understand this paradox, we must look to the origins of the universe, specifically to the Big Bang. In this event, around 13,800 billion years ago, everything we know was created from an infinitely dense and hot point. But what does this mean for the state of the universe at that moment? The answer may lie in how we interpret time and entropy in those early moments. One possibility is that, at the moment of the Big Bang, entropy did not behave in the same way it does today. In that primordial instant, time and space were concepts that were still forming, suggesting that the laws of physics as we know them had not yet been fully established. This leads us to wonder, could there have existed a different kind of order? One that was not governed by the same rules we know? Furthermore, some scientists propose that the low entropy of the primitive universe could be linked to the quantum nature of matter. In those early moments, particles behaved strangely, in a state of superposition and entanglement. Could it be that this quantum state allowed for an organization that, on a large scale, manifested as an ordered universe? The idea is tempting, but it also raises more questions. If the universe began with such order, what happened for it to reach the state of disorder we observe today? The low entropy paradox also forces us to consider the nature of time itself. If time as we understand it is a measure of change and disorder, how does it fit into a universe that began in a state of low entropy? Some theorists suggest that time may have behaved differently in those initial moments. Was time linear, or was there a component of randomness that made it less predictable? Delving into this idea, it is worth exploring the concept that time may not be a universal constant, but rather an emerging property that arises as the universe evolves. If time was not linear at the moment of the Big Bang, could it be that events did not unfold in the way we imagine? This perspective not only challenges our notions of entropy, but also invites us to rethink how we relate to time itself. The low entropy paradox also has profound philosophical implications. If the universe began with such extreme order, does this mean there is a purpose behind its creation? The quest for answers to this question leads us to reflect on the balance between chaos and order in the cosmos. Is the disorder we see today an inevitable phase in a larger cycle of order and disorder? Scientists continue to investigate the phenomenon of low entropy, and although there are still no definitive answers, each discovery brings us a little closer to unraveling this primordial mystery. As we delve deeper into the study of the cosmos, we realize that each question about the origin of time and the universe leads us to more questions. This pursuit of knowledge is, in itself, part of a fascinating process that reflects human curiosity and our desire to understand our place in the vast universe. The low entropy paradox is just one of the many enigmas that arise when examining the beginning of time. As we explore further, we find the need to intertwine concepts from physics, philosophy, and cosmology. The search for answers to these questions not only illuminates the mysteries of the universe, but also invites us to contemplate the deeper meaning of our existence. In considering this paradox, we confront the awe and wonder of the unknown. How can such a vast and complex universe have begun with such perfect order? The exploration of these questions takes us on a journey through time and space, where order and chaos coexist in a cosmic dance. In the end, perhaps the true essence of the low entropy paradox is not just an intellectual challenge, but an invitation to continue exploring the mysteries that surround us. If you're enjoying this journey through the universe and want to keep exploring more cosmic mysteries, don't forget to subscribe to the channel and give the video a like. Thank you for being part of this Star Odyssey. What if I told you that, in the early moments of the universe, time did not flow as we know it today? During that primordial period, the laws of physics as we understand them could have been completely different. But what does it really mean for time to be discontinuous or fluctuating? How can we conceive of a time that does not advance in a linear fashion? The idea of quantum time raises fascinating questions. At the quantum scale, subatomic particles do not obey the conventional rules of physics. Instead of having defined and predictable trajectories, they seem to behave erratically, as if existing in multiple states at once. Could it be that, in that initial period, time itself experienced this same uncertainty? Imagine a universe where each moment is not a firm step forward, but a chaotic dance of possibilities. Imagine that time in its most primitive essence, was more of a field of opportunities where each instant could be a fork in the road. In this context, it is not just about what happened in those early moments, but how time itself could have been in a state of superposition. Just like particles in quantum mechanics, could time have been deciding its own flow? This concept may seem strange, but some suggest that time in the early moments of the universe did not behave like a flowing river, but rather like a sea of waves in constant motion. How did time stabilize to become what we know today? The transition from an unstable quantum state to a linear and coherent time is one of the great questions that still remain unanswered. One of the theories that attempts to address this issue is quantum gravity. This theory seeks to unite Einstein's general relativity, which describes gravity and spacetime, with quantum mechanics, which governs the behavior of subatomic particles. But how do these two seemingly opposing realities intertwine? Is it possible that gravity played a crucial role in the fixing of time, transforming it from a chaotic state to a more structured one? As the universe expanded, it may have reached a point where interactions between particles and forces began to stabilize time. But what drove that stabilization? Some scientists suggest that energy and matter began to organize themselves, and in that process, time acquired a direction. But why is that direction one way? Why does time move forward and not backward? The answer may be related to entropy, which is the measure of disorder in a system. In the early moments of the universe, the state was one of almost perfect order, but as it developed, entropy began to increase, thus defining the flow of time toward the future. But why should we accept that time must follow a path of increasing disorder? Could there be a universe where entropy decreased, allowing time to flow in both directions? The idea of quantum time also opens the door to the possibility of multiple flows of time. If time is not a straight line but rather a set of possibilities, what implications would this have for our understanding of the universe? Could there be other universes where time functions differently? These are questions that challenge our perception of reality. Another intriguing aspect is the initial singularity, that point where everything we know was concentrated in an infinitely small space. At that point, time and space as we know them collapsed. But what happens in a singularity? The laws of physics seem to break down, and time may not exist at all. Is it possible that time as we understand it made no sense in that context? As we explore these ideas, it is fascinating to think about the role that consciousness plays in the perception of time. If time is a construct, how does it relate to our subjective experience of reality? Is it possible that our understanding of time is limited by our own perception? Science and philosophy often intertwine in this realm, challenging our preconceived notions. Every answer we find to these questions leads us to new questions, creating an endless cycle of curiosity and exploration. What else lies hidden in the depths of quantum time? What other mysteries await discovery as we delve into the origins of the universe? Exploring time in its most primitive stages is not only a journey into the past, but also a reflection on our own existence. How does it affect us to understand that time might not be what we think? Each discovery invites us to reconsider our place in the cosmos and the very nature of reality. In the end, the idea of quantum time reminds us that, while we seek definitive answers, the universe is an enigmatic and ever-changing place. The quest for truth about time is, in itself, a fascinating journey that connects us with humanity's deepest questions. In the fascinating journey towards the origin of time, an intriguing question emerges. How did the laws of quantum mechanics and gravity come together to give rise to what we know as time? This enigma has captured the attention of scientists and philosophers alike, challenging our understanding of reality and the universe. To understand this connection, we must first consider what gravity is. In simple terms, gravity is the force that attracts celestial bodies to each other. However, quantum mechanics operates in a different world, where subatomic particles behave in ways that often seem contradictory and random. How can these two realities coexist? The answer lies in the search for a unifying theory. one that combines these two seemingly opposite aspects of physics. What happened in the first moments of the universe? At the moment of the Big Bang, the universe was in an extremely hot and dense phase. At that instant, the laws of physics as we know them began to take shape. But how is time established when everything we know was concentrated in a single point? This is where the ideas of quantum gravity come into play. Attempting to explain how gravity interacts with quantum mechanics, some scientists propose that time is not a continuous line, but rather a series of discrete events that intertwine. In this context, time could be seen as a fabric woven into the tapestry of space. But what does this mean for the way we live and experience time? Our sense of linear time may be an illusion, a construct of our consciousness that adapts to a much more complex reality. Quantum gravity also suggests that space and time are intimately linked. But how can we visualize this? Imagine a surface where each point represents an event in time. As those points intertwine and connect, they begin to form a network. This network expands and contracts, creating what we might consider the flow of time. However, in this scenario, is there a beginning or an end? Or perhaps time is cyclical, an eternal loop that never ends. One of the most intriguing theories is that of multiple universes. If other universes with different laws of physics existed, what implications would this have for our understanding of time? It could be that in those universes, time does not flow in the same way it does in ours. This leads us to wonder, is time a universal property, or does it depend on the context in which it exists? Physicists have also explored the idea that time could be an emerging illusion, a product of quantum interactions at fundamental levels. But how could something as fundamental as time be an illusion? If we consider that our perception of time is influenced by events in our environment, then what if time itself is the result of the interactions of particles in the universe? Quantum gravity, in attempting to unify such fundamental aspects of physics, also faces conceptual challenges. For example, how can time be both a dimension and an emerging property? These questions lead us to reflect on our own existence and our relationship with the universe. Are we really living in linear time? Or are we simply perceiving a sequence of events through our consciousness? As science advances, new theories emerge, such as the idea that time could be related to entropy, the degree of disorder in a system. But what does this mean for our understanding of the beginning of time? If the universe began in an ordered state, how did it evolve into the chaos we see today? This paradox raises the possibility that time, as we know it, is intrinsically linked to the evolution of the universe. All of this leads us to a fascinating conclusion. Time is a more complex concept than it seems. It is not just a line extending from the past to the future, but a multifaceted phenomenon that continues to challenge our understanding. Could it be that time as we understand it is just a small part of a much larger puzzle? As we reflect on the relationship between quantum gravity and time, it becomes clear that the journey towards understanding our universe is a path filled with uncertainties and wonders. Each discovery brings us closer to unraveling the mysteries surrounding the beginning of time, while simultaneously leaving us with more questions. What other truths await us in this vast cosmos? The search continues, and each answer invites us to delve even deeper into the secrets of the universe. What if I told you that at the dawn of the universe there was a moment when space and time experienced an expansion so accelerated that it seemed to defy all known laws of physics? This phenomenon is known as cosmic inflation, and it is one of the most fascinating concepts that attempts to explain the beginning of time. But what exactly is cosmic inflation, and how does it relate to the creation of the universe? Cosmic inflation refers to an extremely short period, just a moment during which the universe expanded at an unimaginable speed. In that brief span, our cosmos went from being smaller than a grain of rice to encompassing vast regions of space in the blink of an eye. But why is this event so important? The answer lies in the fact that this phenomenon not only explains the uniformity we observe in the distribution of matter and energy in the universe, but it also raises profound questions about what happened in those first seconds. Can you imagine what the universe was like at that moment? Instead of the vast and complex structure we observe today, it was an extremely hot and dense place where particles were so close to each other that their interactions were constant. However, this primordial state did not last long. As the universe expanded, it began to cool, allowing particles to come together and form the first atoms. But what triggered this rapid expansion? Scientists are still investigating the causes of cosmic inflation. One of the most accepted theories suggests that a form of energy, known as inflationary energy, played a crucial role. This mysterious energy would have acted as a motor driving the expansion of the universe. But where did this energy come from, and why did it activate at that particular moment? These are questions that remain at the center of scientific debate. Some researchers have proposed that cosmic inflation could have been triggered by quantum fluctuations. This means that in the vacuum of space, small variations in energy could have led to the explosion that initiated the expansion. But what implications would this have for our understanding of reality? If the vacuum can generate energy capable of creating entire universes, what other surprises does the cosmos hold for us? Inflation not only explains the expansion of the universe, but also helps to solve a puzzle: the horizon problem. This puzzle arises when observing that regions of the universe that have never been in contact appear to have identical properties. Cosmic inflation suggests that these regions were once together before being separated by rapid expansion. But how can we verify that this actually happened? Scientists use observations of the cosmic microwave background radiation, a kind of echo of the Big Bang that fills the universe. By studying small variations in this radiation, researchers can infer details about inflation and its impact on the structure of the universe. However, although these observations are fascinating, they still do not provide definitive answers. Could it be that we will never fully understand what happened in those early moments? Cosmic inflation also raises questions about the nature of time itself. During that moment of expansion, time as we know it may have functioned differently. Some theoretical physicists suggest that at that moment, time was not linear and could have been bent or even frozen. Imagine a time that does not flow in a single direction but behaves in completely unexpected ways. How would this change our perception of reality? But not everything can be explained solely by cosmic inflation. There are theories that postulate that the universe could have gone through cycles of expansion and contraction, suggesting that our current universe might be just one of many. Thus, inflation would not only mark the beginning of our universe, but could also be part of a continuous and cyclical process. Are we living in an infinite cycle of births and deaths of universes? As scientists continue to investigate cosmic inflation, new questions also arise. What role does dark energy play in this process? Some believe that dark energy, that mysterious force that seems to be accelerating the expansion of the universe, may have influenced the initial inflation. If this is true, the connection between inflation and dark energy could open new avenues of research regarding the fate of the universe. Ultimately, cosmic inflation is a reminder of the wonder and complexity of the cosmos. It invites us to question what we know and to explore the unknown. With each discovery, we get a little closer to unraveling the secrets of the beginning of time, but we also face new uncertainties that challenge our understanding. The quest to comprehend this primordial moment continues, and with each answer, more fascinating questions arise. So the next time you look up at the starry sky, remember that at the heart of those stars, in the whisper of the cosmos, lies the story of a universe that began in an explosive and mysterious way. Cosmic inflation is just one of the many pieces of this puzzle, and each of them brings us a little closer to understanding how it all began. Are you ready to keep exploring these mysteries of time and space? What does it really mean to create something from nothing? This question has intrigued philosophers, scientists, and thinkers throughout history. When we reflect on the beginning of time, we face a surprising paradox. How can something arise from nothing? When we talk about the origin of time, we often encounter the idea that before the Big Bang there was only emptiness, a state in which even the laws of physics did not exist. But is it possible that this nothingness had some kind of hidden potential? Creation from nothing is not only a philosophical concept but also a scientific challenge. Imagine a universe where neither space nor time existed. How can existence be understood if there was nothing to be understood? This dilemma leads us to explore theories that attempt to unravel the mystery of how time and consequently the universe could have emerged. Some of these theories suggest that the Big Bang was not a true beginning but rather the result of a more complex process. An intriguing concept is the idea that the universe could have emerged from a quantum vacuum state, where particles and antiparticles constantly appear and disappear. But what does this really mean? For some, this vacuum is not the absolute nothingness we imagine, but rather a state full of potentiality. Could it be that the vacuum is in some way alive and filled with possibilities waiting to manifest? Some scientists propose that in that primordial nothingness before time began, there was a quantum fluctuation that gave rise to creation. This suggests that time and space are not pre-existing conditions but emerged from a quantum state where everything was possible. But how can something as complex as time arise from such an apparently simple state? This is one of the great mysteries that physicists are trying to solve. Creation from nothing also raises questions about causality. If there was nothing before the Big Bang, what caused it to happen? Can there be effects without causes? This is one of the most challenging questions in cosmology. The notion that time and space could have originated from an event that has no clear cause leads us to rethink our ideas about the universe and how it works. Moreover, philosophy plays an important role in the discussion about creation. Is it possible that time and space are constructs of the human mind, ways in which we try to understand the incomprehensible? Some thinkers argue that time may not be an absolute entity, but rather a conceptual tool we use to navigate our experience of reality. This opens the door to a multitude of questions such as, what lies beyond our understanding of time? Let us imagine that time is not a straight line from the past to the future, but rather a multi-dimensional fabric where each moment is interconnected. Could it be that our perception of time as linear is an illusion? This idea leads us to reflect on how time influences our lives and our understanding of the universe. On the other hand, some theorists suggest that time could have a cycle rather than a defined beginning and end. This aligns with the Big Bounce hypothesis, which proposes that our universe could have emerged from a previous collapse. If this is true, then time could be an endless cycle of creation and destruction. What implications would this have for our understanding of existence? The idea that time could be eternal or cyclical also has profound philosophical implications. Does this mean that time is infinite and that there will always be something, in one sense or another? Or are we doomed to live in a universe that has a final destiny? These questions are not only intriguing from a scientific perspective, but also touch the deepest fibers of our existence. In the end, when contemplating creation from nothing, we are faced with a mystery that we may never fully resolve. Science advances, and with it, our understandings and theories about the universe and time. However, as we delve deeper into these questions, we not only expand our knowledge, but also venture into the very heart of what it means to be human, the quest for answers in a vast and mysterious cosmos. Creation from nothing is not just an academic topic, it is a philosophical and scientific journey that invites us to question our most fundamental assumptions. Are we prepared to accept that we may never fully understand the origin of time? Perhaps in the end, what matters most is not finding definitive answers, but continuing to explore the mystery that surrounds us. Thus, creation from nothing becomes one of humanity's great legacies. Curiosity and the desire to understand our place in the universe. The arrow of time, that mysterious phenomenon that marks the course of our lives, becomes an enigma when we try to understand why time flows in only one direction. What establishes this direction? Why can't we simply reverse the flow of time as if we were rewinding a movie? To understand it, it is essential to explore the concept of the arrow of time and how it manifests in our universe. In everyday life, we perceive time as a river that moves forward incessantly. From the moment we are born to the instant we depart, each experience piles up in a sequence that seems unchangeable. But is time really a straight line? Or perhaps are there more ways to understand it? This is a question that has fascinated philosophers, scientists, and the curious alike throughout history. One of the first clues about the nature of time can be found in the second law of thermodynamics. This law states that in a closed system, entropy, or disorder, tends to increase over time. In other words, chaos takes over everything we know. Imagine a glass that shatters. The fragments on the floor represent a state of greater disorder than the intact glass. Thus, time moves toward greater disorder, and this could be what gives rise to our perception that time only flows in one direction. But what happened in the early moments of the universe? Back then, everything was much more ordered. Matter and energy were organized in a way that challenges our current understanding. How is it possible that such an ordered universe could give rise to a future full of chaos? This paradox becomes the key to understanding the arrow of time. Moreover, there is another facet of time that complicates things even further: Einstein's relativity. According to his theory, time is not an absolute concept but is altered by speed and gravity. This means that two observers can experience time differently. If we travel at speeds close to the speed of light, time dilates. What implications would this have for our understanding of the arrow of time? Could it be that in reality, time has multiple arrows depending on how it is observed? On the other hand, quantum mechanics also introduces its own dose of mystery. At tiny scales, time seems to behave strangely. Subatomic particles can exist in multiple states at the same time, raising the question, is time an illusion in the quantum world? Could there be a time that behaves differently from what we experience in our daily lives? As we delve deeper into these concepts, more questions arise. Why can't we remember the future? Is it possible that time as we understand it is a construct of our mind? If time is a direction, what about the past? Memory plays a crucial role in how we experience time, and it is possible that our perception of the past is simply a narrative constructed by our brain. In the realm of cosmology, the arrow of time is also related to the expansion of the universe. As the cosmos expands, time unfolds with it. This expansion not only affects matter but also influences how we experience time. Could it be that the direction of time is intrinsically linked to the expansion of the universe? It seems that a new horizon of questions arises that challenges our current understanding. Reflecting on the arrow of time, we find that it is not just a scientific issue but also a philosophical one. What does it mean for us as conscious beings to know that time moves toward disorder? How does this affect our perception of life and death? Understanding our existence in an expanding and disordering universe can be both terrifying and liberating. Ultimately, the arrow of time remains a mystery. As we explore the frontiers of physics and cosmology, more questions than answers present themselves. The quest to understand time and its direction is a journey that takes us to the limits of science and philosophy. And although we may not have all the answers, each discovery brings us a little closer to unraveling one of the greatest mysteries of existence, the flow of time. So the next time you look at a clock and see the hands moving forward, remember that time is not just a measure, but a complex and fascinating experience. What secrets does time hold? Is there more than we can imagine? The exploration continues, and with each new hypothesis, we delve deeper into the depths of this cosmic enigma. The arrow of time, though a mystery, is a reminder of our endless pursuit of knowledge and understanding in a universe that never ceases to surprise us. What really happened at the zero moment when the universe began to exist? For many, this is one of the most fascinating and perplexing questions in cosmology. In the blink of an eye, everything we know and understand about time, space, and matter originated from a point that, according to current theories, was infinitely small and dense. But how can something so complex arise from such a singular instant? The notion of the zero moment is intriguing. It is the moment when nothing existed, and yet from that absolute void, everything emerged: galaxies, stars, planets, and of course life. But how can we understand something so abstract? What does it really mean that time and space were born from nothing? Can nothing, in its purest essence, be the origin of everything we know? For many scientists, the zero moment is a great mystery. Some argue that before that moment there was neither time nor space. Which raises the question, how can there be a before without a temporal context? This paradox leads us to explore the nature of time itself. If time began with the Big Bang, what do the concepts of cause and effect mean in a context where there was nothing to cause anything? Imagine if the universe existed in a state of potential where all possibilities were contained in that point of singularity. Could it be that the zero moment was not just the beginning, but a moment of radical transformation, where the laws of physics as we know them began to take shape? This suggests that what happened at that moment was more than a simple explosion. It was the creation of a stage where the rules of the universal game were established. Moreover, the concept of initial singularity leads us to think about the very nature of reality. What does it mean that the entire universe was concentrated in such a tiny point? Was this point a field of pure energy? An explosion of limitless potential? This kind of questioning pushes us to the limits of our understanding and leads us to question the very nature of existence. Shortly after the zero moment, the universe began to expand at unimaginable speeds. This expansion not only created space, but also generated time. But how does that translate in terms of our daily experience? When we say that time began, does it mean that before that moment there was nothing? Not even the possibility of measuring time? Every attempt to visualize the zero moment leads us into a labyrinth of paradoxes and speculations. Some scientists suggest that at that primordial moment, the laws of physics we know did not apply, making it difficult even to imagine how it could have happened. Was the universe a vast ocean of possibilities that eventually materialized into the reality we know today? As we explore these questions, we find that the zero moment is not just a physical concept, but also a philosophical one. It invites us to reflect on our own existence and the place we occupy in the vast cosmos. What does it mean to be part of a universe that was born from nothing? Could it be that this mystery is an invitation to understand not only the cosmos, but also our own human nature? The zero moment also leads us to consider the idea of cycles in time. Some theorists suggest that the universe may not have had an absolute beginning, but could be part of an endless cycle of expansion and contraction. If this is true, does it mean that the history of the universe is a continuous loop? Are we living a version of a cycle that repeats eternally? In this exploration, the concept of creation from nothing becomes a central theme. How can something arise from complete absence? Modern physics challenges us to accept that existence itself may be stranger than we ever imagined. In this sense, the zero moment is not just a moment of beginning, but a window into the very essence of reality. As we delve deeper into the mystery of the zero moment, we find that human curiosity to understand the universe is inexhaustible. Every answer generates new questions. What does time really mean if it began at that moment, and what does that tell us about the future of the universe? The quest for answers about the zero moment may lead us to discover not only the origin of the cosmos, but also to rethink our own perception of time and existence. The zero moment is a reminder that, at the heart of the universe, there is a profound mystery that we have yet to fully decipher. Every discovery about the origin of time brings us a little closer to understanding not only the cosmos, but also our own history. So what does the future hold for us when we finally unveil the enigma of the beginning of everything? The adventure is just beginning. What exactly is the initial singularity? Imagine a point where all matter, energy, space, and time are concentrated in an infinitesimal amount. This concept may seem like something out of a science fiction movie, but it is the foundation of our understanding of the birth of the universe. At this point of infinite density, the laws of physics as we know them break down. But how can everything we see today come from something so extraordinarily small and dense? The initial singularity is the heart of the Big Bang, the event that initiated everything. But what happened at that moment? Current theories tell us that at that time everything was compressed into a tiny sphere, where time and space had no meaning. However, questions arise. If everything was in a single point, how did it then expand? What triggered that initial explosion that transformed the singularity into the vast universe we know today? Some scientists suggest that time as we understand it did not exist at the singularity, so could time have begun at the very moment the universe began? This idea challenges our everyday perception of time. Normally we see it as a continuous line moving forward uniformly, but if time began at the singularity, how can that moment be measured? Curiosity about the singularity also leads us to think about the nature of gravity. How does gravity behave in a place where everything is infinitely dense? In the singularity, the gravitational force becomes so intense that even light cannot escape. This raises another big question. If light cannot escape, how can we know what happened at the moment of the Big Bang? The answer is that we cannot, at least not with the physics we know today. Still, some theories suggest that there could be quantum fluctuations at the singularity that might have led to the expansion of the universe. But what does this mean for us? If the universe began from these fluctuations, perhaps chaos and order are two sides of the same coin that has been playing since the dawn of time. The initial singularity also raises philosophical questions. If everything that exists today originated from a single point, does this mean that the universe is finite? Or is there something beyond what we can see and measure? The idea that everything comes from a singularity may make us feel small, but it also invites us to explore beyond the obvious. And when we talk about the singularity, we cannot help but wonder about the future. If everything began in a single instant, will the universe have an end? Could there be a return to that singularity, a collapse that restarts the cycle of time? This idea intertwines with the Big Bounce hypothesis, which suggests that the universe could expand and contract in infinite cycles. As we explore these concepts, we must also consider that our understanding of the universe is limited. Current theories are just that, theories. The initial singularity remains one of the greatest mysteries in modern cosmology. As scientists continue to investigate, could we someday unravel the secrets of that first moment? Each discovery in this field opens up new questions. The initial singularity is not only a topic of conversation among scientists, but also leads us to reflect on our existence and the place we occupy in the cosmos. Are we truly alone in this vast universe, or are there other places where singularities might have given rise to completely different realities? The singularity is both an end and a beginning, a point where the rules of the universe are rewritten. And although we do not have all the answers, the pursuit of knowledge is what drives us forward. Human curiosity has been the engine that has taken us to explore the far reaches of space and time, and the initial singularity is one of the most fascinating paradoxes that invites us to keep probing. As we reflect on these questions, we must also remember that the journey to understand the initial singularity is as important as the answers themselves. In every question we pose, every theory we develop, we are one step closer to understanding not only our universe but also time itself. What other secrets does the singularity hold for us? This is an adventure that is just beginning and invites us to continue exploring the limits of our understanding. What if I told you that time as we know it may not have always been linear? Stephen Hawking, one of the brightest physicists of the 20th century, proposed a fascinating idea that could change our understanding of time. In his theory, primitive time was not a straight line moving forward, but could have had a curved shape, almost like an expanding bubble. But how is it possible for time to be something more than a simple sequence of events? Imagine a moment when the boundaries of time blur. In this sense, Hawking's notion of imaginary time invites us to rethink our perception. But what does imaginary time really mean? In physics, this concept is used to describe a space where time does not behave as we understand it. Instead of flowing from a past to a future, this time becomes a dimension that can curve, interrelating in ways we have yet to fully comprehend. This idea may seem strange, but it is an attempt to solve some of the most complex problems in cosmology. If time is curved and not linear, what implications does this have for the beginning of the universe? Does it mean that the Big Bang was not necessarily the absolute beginning, but rather an event within a broader cycle of expansion and contraction? The notion of imaginary time opens the door to fascinating questions about what existed before the Big Bang. One of the challenges we face in exploring this theory is understanding how it fits with what we know about gravity and quantum mechanics. If time is not linear, how do the laws of physics relate in this context? Gravity, as we understand it, is closely linked to the structure of space and time. But what happens when those structures become distorted and time behaves differently? The idea that time could be imaginary also invites reflection on the nature of reality itself. If time is merely a projection of a more fundamental state, could it be that our everyday experience of time is just an illusion? Are we trapped in a linear narrative, while in reality the universe operates in much more complex ways? Hawking suggests that in a universe where time is imaginary, we might find answers to some of the deepest questions about existence. For example, if time does not have a beginning in the traditional sense, could it be that there has always been something, even in the absence of linear time? This idea is unsettling, as it challenges our understanding of causality and sequentiality. When thinking about imaginary time, it is easy to feel lost between theory and reality. But there is something profoundly appealing in how it pushes us to question everything we think we know. Is time really an arrow moving forward? Or could it be a cycle in which moments intertwine and repeat in unexpected ways? This perspective may seem like a labyrinth, but it is also a path toward new ways of understanding the universe. The beauty of Hawking's theory lies in its ability to interconnect different threads of cosmology. It invites us to consider the possibility that time, in its purest essence, is not a scarce resource that is spent as we move forward, but a dimension in constant interaction with the matter and energy surrounding it. This raises an interesting question. If time is curved, how does this influence our perception of life, change, and destiny? As we explore these ideas, it is important to recognize that imaginary time is not just a scientific curiosity. It also has profound philosophical implications. If time is not linear, how does this affect our beliefs about the past, present, and future? The way we conceptualize time can change our relationship with life itself and how we approach the decisions and events that affect us. As we continue to delve into imaginary time, let us remember that each answer may lead to new questions. Science is a journey, and each theory we explore brings us a little closer to understanding the mysteries of the universe. Perhaps the key to unraveling the beginning of time lies in accepting that there are aspects of reality that may be strange and counterintuitive. Ultimately, Hawking's theory of imaginary time challenges us to look beyond what we see. It invites us to be curious, to explore the realm of the unknown, and to let our imaginations soar. If time can be imaginary, what other wonders of the universe are waiting to be discovered? The search for answers continues. And each discovery brings us one step closer to unveiling the secrets that have been hidden since the dawn of time. Dark energy is one of the great mysteries of the universe, but what is it really? To understand its possible influence in the early moments of existence, it is essential to explore what is known about this enigmatic force. Dark energy represents approximately 70% of the total content of the universe. However, it remains a puzzle in many respects. Could it have played a crucial role in the beginning of time? Let us imagine for a moment the universe shortly after the Big Bang. At that instant, everything we know was concentrated in an extremely small and hot point, but what happened in those early moments? Some scientists suggest that dark energy may have played an essential role in the expansion of the universe. But how is it possible that something as abstract as dark energy influenced time itself? To understand this phenomenon, it is important to consider that dark energy does not act like the matter we know. While matter has gravity and tends to attract other masses, dark energy seems to have the opposite effect. Instead of attracting, it pushes, accelerating the expansion of the universe. This unusual behavior raises fascinating questions about how it could have affected the earliest moments of time. Is it possible that this energy, by pushing space, facilitated the creation of time as we know it? The accelerated expansion of the universe is a concept that challenges our understanding of the cosmos, but what does this mean for time? If the universe was expanding faster than could be measured, how were the limits of time defined? Perhaps in those primordial moments, the relationship between space and time was very different from what we understand today. Dark energy, with its ability to alter the structure of space-time, could have played a fundamental role in creating a framework in which time could exist. Delving deeper into this idea, another intriguing question arises. Could dark energy be responsible for the arrow of time? The concept of the arrow of time refers to the direction in which time flows from the past to the future. Some scientists believe that dark energy could have influenced this flow, establishing a clear direction for time from the very beginning of everything. As we explore further, we find theories suggesting that dark energy could be connected with quantum gravity. This is one of the most complex areas of modern physics, where attempts are made to unite the theories of relativity with quantum mechanics. In this context, dark energy could have been a key factor in establishing time and space, allowing both realities to coexist in an expanding universe. Dark energy also raises questions about the very nature of the universe. If it has been present since the beginning, does this mean that time itself is a product of its influence? Some physicists suggest that if dark energy is constant, it could have established a background for time, allowing it to flow coherently through the vast expansion of the cosmos. But what if dark energy is not constant? If its nature changes over time, this could have significant implications for the future of the universe and time itself. Imagine a scenario where dark energy begins to decrease. How would this affect the flow of time and the structure of the universe? The possibility of a change in dark energy could open the door to new ways of understanding time and its relationship with the cosmos. In this context, it is interesting to reflect on the role of dark energy in the creation of cosmic structures. From galaxies to galaxy clusters, dark energy could have influenced how large structures in the universe group together. As the universe expands, so does the influence of dark energy. This leads to questioning how time developed in relation to the birth of these structures. In the end, dark energy remains a mystery. Could it be that ultimately this enigmatic force is telling us something about the nature of time itself? Perhaps as we continue to explore the cosmos and its secrets, we will discover that dark energy is not only a force that accelerates expansion, but also an essential component in understanding time and its beginning. The study of dark energy and its possible influence on the beginning of time leads us to reflect on our own existence. If dark energy played a crucial role in the creation of time, then it could be a fundamental piece in the puzzle of cosmology. As we advance in our quest for answers, we may find that time, with all its complexities, is intrinsically linked to the nature of the universe and the forces that shape it. Are you ready to continue exploring these mysteries and discover how time and the cosmos intertwine? The universe is a vast mystery, and one of the most fascinating enigmas is undoubtedly the horizon problem. How is it possible that regions of the universe that are so far apart can be so perfectly synchronized? To understand this, it is necessary to go back to the earliest moments of the cosmos's existence, when everything was in a kind of primordial soup. But what does this really mean? Imagine a universe that, in its first moments, was so small and dense that the laws of physics we know were just beginning to take shape. In that environment, particles were so close to each other that they could interact in ways we cannot observe today. However, as the universe began to expand, these regions moved away from each other at an incredible speed. But here comes the crucial question. If light, which travels at a finite speed, did not have enough time to cross those vast distances, How could the young universe know what was happening in other parts? The answer to this intriguing question may lie in the theory of cosmic inflation. This concept suggests that just after the Big Bang, the universe underwent exponential expansion. In an incredibly short time, the universe expanded so rapidly that parts that were once in contact became completely separated. But what does this mean for the horizon problem? Is it possible that this expansion created a state in which distant regions of the universe could, in some way, share information? To complicate matters further, we must consider that, in those early moments, the universe was not only expanding but also filled with energy. This energy, which would eventually become matter, could have influenced how particles interacted with each other. Could it be that the interactions in that primitive state of the universe were powerful enough to allow information to be transmitted instantaneously across distances that today seem insurmountable? Scientists often refer to this phenomenon as the correlation effect. Essentially, it means that although two parts of the universe are separated, they can be correlated in ways we do not fully understand. But how does this translate into simple terms? Imagine a group of friends who, without communicating, seem to know what each other is thinking. How is that possible? Perhaps there is something deeper that eludes our understanding. The horizon dilemma leads us to question not only how the universe synchronized, but also how the structures we see today formed. Galaxies, stars, and planets are the result of a complex and fascinating process. But if regions of the universe were so separated, how could these structures form so uniformly? It's as if each part of the universe were following a perfect choreography, don't you think? Some theoretical physicists suggest that, despite the distance, there were energy fields permeating the universe, connecting different regions in ways we still do not understand. This concept is intriguing, but also raises more questions. Could there be some kind of underlying network that unites the entire cosmos? If so, what implications would that have for our understanding of time and space? Another related idea is that of multiple universes. Some scientists speculate that there could be other realities, other dimensions, where the laws of physics are different. In those universes, time might flow in ways that challenge our logic. What would it be like to live in a universe where time is not linear? Would we be able to experience causality in the same way we do here? As we explore these ideas, we realize that the horizon problem not only raises questions about the synchronization of the universe, but also touches on our understanding of causality. If there is not enough time for interactions to occur, then how can we talk about cause and effect in the early moments of the universe? This is one of the deepest questions physicists face today. It is fascinating to think that while we are trying to understand the beginnings of time, there is still so much we do not know. Science advances, and each discovery reveals new layers of complexity. But will we ever fully understand the horizon problem? Perhaps the answer lies beyond our capacity for comprehension. What is clear is that the universe is a mysterious place full of secrets waiting to be uncovered. The horizon problem is just one example of how many questions remain unanswered. Each of us, when contemplating the cosmos, becomes part of this endless quest for knowledge. As we reflect on these issues, it is important to remember that each answer we find leads us to new questions. This is the true spirit of science, a constant exploration in search of understanding the unknown. So what will the future tell us? Will we finally unravel the enigmas of time and the universe? Only time will tell, and that, ironically, is part of its own mystery. Is it possible that there are parallel worlds where time behaves differently than ours? This question has intrigued scientists and philosophers for generations, and today we delve into theories that suggest time is not a unique experience but could vary from one universe to another. Imagine a multiverse where each universe operates under its own physical laws, leading to different realities and time flows. What implications would this have for our understanding of time and existence itself? In this vast cosmic scenario, each universe could have its own clock, marking the passage of time in ways we can barely begin to imagine. What would life be like in a universe where time moves faster or slower? Perhaps in that universe, events that we consider historical could unfold in the blink of an eye. The idea of divergent times poses a fascinating mystery. If time is a constant in our universe, what makes it so special? On the other hand, the notion that time could be different in other universes also raises questions about causality. In our universe, we know that an effect requires a cause, but what if this were not the case in another universe? In an environment where time behaves non-linearly, the relationships of cause and effect could become blurred. Are we prepared to accept that our notions of past, present, and future may not be universal? Some theories suggest that these parallel universes, if they exist, could interconnect in ways we do not fully understand. Imagine that at some point one universe could leak into another, creating shared experiences that challenge our physical laws. Could it be that in those encounters, time itself is altered? This intertwining of realities opens the door to extraordinary possibilities, where the boundaries of our temporal experience become blurred. However, science has yet to provide concrete evidence of these parallel universes. Nevertheless, quantum mechanics, with its strange and often illogical nature, offers fertile ground for speculation. In this realm, Heisenberg's uncertainty principle suggests that particles can exist in multiple states at the same time. Could it be that time, like these particles, has multiple forms of existence? The idea of parallel universes is also related to the many worlds interpretation of quantum mechanics. According to this interpretation, every decision we make could lead to a branching in time, creating a new universe with its own temporal flow. Thus, each moment of choice could give rise to completely different realities. Does this mean that somewhere there exists a you who made different decisions, experiencing a different time? As we explore this idea, we encounter the challenge of perception. If time is subjective, as suggested by the theory of relativity, could our experience of time be limited by our position in the universe? In this sense, time could be a more flexible phenomenon than we imagine, allowing for radically different perceptions of time in other universes. Is it possible that time is an illusion, a construct of our mind manifesting differently in other places? Some scientists suggest that the existence of parallel universes could help explain astrophysical phenomena that we do not yet understand. For example, dark matter and dark energy are components that seem to challenge our notions of physics. Could these mysterious forces be manifestations of alternative universes interacting with ours? This connection could offer answers to questions that have puzzled science for decades. However, the idea of parallel universes also raises ethical dilemmas. If every decision creates a new universe, what does this mean for our actions and responsibilities? Can we live our lives thinking that there will always be an alternative version where our choices are different? Moral responsibility can become complex in a multiverse where every action echoes in parallel realities. The exploration of these concepts is not limited to physics. It also opens a range of possibilities in philosophy. If time and existence are not linear, what does it mean to be human in a context where each life could be just one of infinite experiences? This reflection invites us to question our relationship with time, our history, and how we perceive ourselves in the vast universe. As we delve into the mystery of parallel universes and their different time flows, it is essential to remember that these ideas, while fascinating, are still hypothetical. Science continues to investigate, trying to unravel these enigmas. Each discovery in the field of cosmology brings us a little closer to understanding not only the beginning of time, but also the essence of our own existence in this vast multiverse. In conclusion, the possibility of parallel universes where time flows differently provides us with a unique perspective on the nature of time and life itself. It challenges us to think beyond our everyday experiences and to imagine a cosmos where the rules we know are just a small fraction of a much more complex reality. Every question that arises in this realm invites us to explore, to dream, and above all, to keep seeking answers in the vast universe that surrounds us. Who knows? Perhaps in some corner of the multiverse, the answers we seek are already waiting to be discovered. The Big Bounce hypothesis proposes a fascinating idea. What if time did not begin with the Big Bang, but is part of an endless cycle of expansion and contraction? How does this notion fit within our understanding of time and the universe? For many, the idea that time may have existed before the Big Bang is perplexing, but it is a concept worth exploring. For decades, scientists have debated the nature of the Big Bang. We all know that this event marked the beginning of our universe as we know it. But what happened before? The Big Bounce hypothesis suggests that the universe has gone through periods of contraction followed by explosive expansions. If this is the case, time could be an eternal cycle, where each end is a new beginning. But how could everything we know have emerged from a previous collapse? Imagine a balloon that inflates and deflates repeatedly. In each cycle, the balloon contracts to an infinitely small point and then explodes again, creating a new universe. However, each time it inflates, it is not exactly the same. There are differences in its fundamental properties. This concept raises intriguing questions. Could there have been universes prior to ours that were different in terms of their physical laws? Or perhaps some of those universes could have harbored life, but under conditions that would never be recognized. Proponents of the Big Bounce argue that if time is cyclical, then cause and effect could take on new meanings. Instead of thinking of the Big Bang as a unique event, we might see it as a phase in an endless cycle. This leads to profound reflections on causality itself. If each universe has its own Big Bang, does this mean that each one also has its own cause? It is fascinating to consider how our notions of beginning and end could change. In this scenario, time is not perceived simply as a straight line moving from an initial point, but rather as a spiral that repeats, where each cycle brings with it a new story. What implications would this have for our understanding of life and existence? If time is cyclical, could it be that our experiences and memories are also connected to previous universes? But what evidence supports the idea of the Big Bounce? Some scientists have explored the properties of matter and energy in the current universe, searching for patterns that suggest a deeper history. Through theories of quantum gravity, models have been proposed that allow for the possibility of a bounce instead of a total collapse. In these models, the conditions of the universe before the Big Bang could have been very different from what we imagine. In this context, it becomes evident that dark energy could play a crucial role. Could it be that this mysterious force was responsible for the expansion after a collapse, pushing the universe into a new cycle of life? Questions arise, and each one opens new doors to curiosity and investigation. On the other hand, the dilemma of causality remains a mystery. If time has always been in a cycle, how can we define a cause for the Big Bang? What does cause really mean in a universe where everything could have existed in an eternal loop? This dilemma invites reflection on the laws of physics and how they might adapt to a cyclical view of time. However, not everyone agrees with the idea of the Big Bounce. Some scientists argue that the Big Bang model, as we know it, is sufficient to explain the creation of the universe. Yet the beauty of science lies in its ability to question, investigate, and redefine our knowledge. Is it possible that in the future new evidence will breathe life into the idea of the Big Bounce and once again change our understanding of time? Moreover, the notion of parallel universes could be related to this theory. If time is cyclical, that could open the door to the existence of multiple realities at different stages of their own cycles. What if in an alternative universe there exists a version of ourselves living in a different cycle? This kind of speculation is not only fascinating but also invites us to think about our own existence and the meaning of being part of this vast cosmos. In conclusion, the Big Bounce hypothesis is a reminder that time and the universe are filled with mysteries yet to be discovered. Although we may not have all the answers, what we do know is that each new idea and each new theory brings us a little closer to understanding our existence. Curiosity and exploration are fundamental engines of knowledge, and each question posed leads us to an even deeper and more complex world. Although time remains an enigma, each discovery allows us to see a little further beyond the veil of the unknown, inviting us to continue questioning and learning about the universe in which we live. What does the concept of causality really mean in the context of the beginning of time? It is a question that has intrigued thinkers and scientists for generations. If time was born in the Big Bang, how is it possible that there are causes for that crucial moment? Delving into this dilemma is like opening a door to a labyrinth of paradoxes and deep reflections. To understand it, we must first consider what causality is. Causality is the relationship between cause and effect. In our daily experience, everything that happens has a reason, a motive behind it. However, when it comes to the beginning of the universe, this logic is put to the test. What could have caused the Big Bang if, at that moment, time itself was just beginning? Is it possible that the concept of cause as we know it does not apply in those circumstances? The idea that time began with the Big Bang poses a fundamental problem. If time did not exist before that event, then any notion of cause also fades away. How could there be something that caused the creation of time? This question generates profound bewilderment and leads us to reconsider our conceptions of reality. Are we limited by our understanding of time and causality? Some scientists suggest that the Big Bang is not the true beginning, but rather a point of transition. In that view, the universe may have had a prior state, a cycle of expansion and contraction. Could it be that time restarts over and over again in an infinite cycle? This proposition, known as the Big Bounce hypothesis, offers a possible way out of our dilemma. If time is cyclical, then the question about the cause of the Big Bang might be misformulated. Instead of looking for a before, we could be observing an eternal return. However, this idea also presents its own challenges. If time is cyclical, does it mean that events repeat exactly in the same way, or are there variations in each cycle? This question leads us to explore the very nature of time. Is time a river flowing in one direction, or rather an ocean of possibilities where each wave is unique? Another approach is to consider the relationship between time and quantum mechanics. In the quantum world, the rules are very different from those we know. Causality in this context becomes more diffuse. Could it be that time and causality are not as absolute as we think? Quantum fluctuations suggest that what we consider a causal event might simply be a series of probabilities at play. Reflecting on the dilemma of causality, one wonders if it is possible that the universe does not need a cause in the traditional sense. Some philosophers and physicists have proposed that the universe could exist without reason. In this scenario, the Big Bang could simply be a spontaneous event, an explosion of possibilities without a why. This provocative idea challenges our search for meaning in the cosmos. Indeed, as we delve into the mystery of the beginning of time, we find ourselves at a crossroads. On one hand, the logic of causality seems to dictate that everything must have an origin. On the other, the universe itself may be challenging this notion. Could it be that time, as we understand it, is a human construct designed to give us meaning in a world that, in its essence, does not follow our rules? It is fascinating to think that as we explore these questions, we are not only unraveling the mysteries of the universe, but also confronting our own limitations as human beings. The search for answers about causality and the beginning of time is, ultimately, an exploration of who we are and our place in the vast cosmos. As we continue this journey, it is crucial to keep an open mind. Perhaps, instead of seeking definitive answers, we should embrace the uncertainty and complexity of these topics. Science and philosophy often intertwine in this quest, and each answer may open new questions. The idea that time and causality may not be as closely linked as we believe invites us to rethink our understanding of the universe. Is it possible that time is something much deeper and more enigmatic than we ever imagined? This reflection leads us to consider that as we advance in our pursuit of knowledge, each discovery could be just a step on an infinite ladder of mysteries. So as we navigate these deep and often murky waters of the beginning of time and causality, it is essential to remember that curiosity and doubt are our best allies. Ultimately, the journey toward understanding is as fascinating as the mysteries themselves that we seek to unravel, and who knows? Perhaps along the way, we will discover not only the secrets of the universe, but also a greater understanding of ourselves and our place within it. How are time and space related? Often we think of time as something linear, an arrow that moves from one moment to the next. But what if I told you that, according to Einstein's theory of relativity, time is more than just a sequence of events? The idea that time depends on space is a revolutionary concept that has changed our understanding of the universe. But how did Einstein come to this conclusion? In 1905, Einstein presented his theory of special relativity. In it, he proposed that time is not absolute. This means that time can pass at different rates depending on the speed at which you are moving. Imagine traveling at the speed of light. For you, time might seem normal, but for an observer at rest, your clock might appear to stop. So, is time really the same for everyone? With general relativity, Einstein took this idea even further. He proposed that time and space are interconnected in a kind of fabric called spacetime. But what does this mean in terms of the creation of time? If spacetime is a single entity, how did it come into being during the Big Bang? It is said that at that moment, time did not exist in the way we know it today. Imagine the Big Bang as a starting point. However, what is intriguing is that before that moment, the concept of time may not have made sense. How can we talk about time if there is nothing to mark it, no event to record it? This enigma leads us to ask what really happened at that zero moment. Einstein's relativity also suggests that gravity can affect time. The closer you are to a massive object, the slower time passes compared to someone who is farther away. This raises another fascinating question. If gravity plays a role in the perception of time, was gravity what helped shape the early moments of the universe? And here arises a crucial question. How are gravity and time related at the moment the universe began to expand? Some theories suggest that, at that precise instant, the laws of physics as we know them may not have had the same meaning. Quantum physics, for example, tells us that particles can exist in multiple states at once. So could it be that time in its early moments was filled with possibilities rather than being linear? On the other hand, time has also been viewed as a continuous flow in the theory of relativity. But is that really the case? Some scientists think that time could be an illusion, a construct of our minds to understand the universe. If time is just a way we perceive the world, what implications does this have for our understanding of the beginning of time? Moreover, there is a connection between time and energy. Relativity tells us that energy can curve space-time. So, in the early moments of the universe, when energy was immense, how did that affect the way time developed? Could it have influenced the creation of structures that we now consider fundamental in the cosmos? We cannot forget the role that matter plays in this equation. Matter and energy are interchangeable, as the famous equation by Einstein, E=mc² states. This suggests that matter, just like energy, could have had a significant impact on the creation of time itself. If matter existed in a primordial form, could it have been the spark that ignited the cosmic clock? As we explore these questions, we encounter the limits of human knowledge. There are theories suggesting that time as we know it could have been created by the interaction of fundamental forces in the universe, but what forces were those? And even more intriguingly, could there have been a time before time? A state of the universe in which time made no sense? When considering relativity and time, we also face the idea of singularity. At the heart of the Big Bang lies a point where the laws of physics break down. What does this mean for our understanding of time? If time originated at this point, could it be that we will never fully understand what happened in that initial moment? The theory of relativity provides us with a framework, but it also leaves us with more questions than answers. How does all this connect with the mystery of time itself? In an expanding universe where time and space are intertwined, can we truly claim that time has a beginning? The search for answers about time and its beginning leads us to reflect on our own existence. As we explore the universe, we realize that time, far from being just a resource, is a fundamental component of reality. How does our understanding of time affect the way we live and view the world? Finally, as we continue to investigate the mysteries of time and space, we face the astonishing reality that each answer may open the door to new questions. Are you ready to keep exploring these mysteries and discover what the universe still has in store for us? At the heart of modern physics, an intriguing concept emerges from the depths of the universe: quantum foam. But what exactly is this quantum foam, and why is it so fundamental to understanding the fabric of space-time? Imagine an incessant sea of bubbles, where reality transforms into something ethereal and fluid. This visual image may seem like it's taken from a science fiction movie, but in the realm of physics, it represents one of the most revolutionary ideas about the nature of the universe. Quantum foam suggests that, at the tiniest scale, space is not a uniform void. Instead, it is filled with fluctuations and variations that occur at an almost incomprehensible speed. But how can something so chaotic shape our universe? The answer lies in the fact that these quantum fluctuations could have given rise to the structures we know today. From the perspective of quantum mechanics, space-time is not just a backdrop where events occur. It is dynamic and reacts to the energy and matter it contains. This raises a fascinating question. If space-time can be so unstable at a microscopic level, could it have influenced the earliest moments of the universe? Imagine that in those primordial instants, quantum foam was a breeding ground for the creation of particles, energy, and eventually, galaxies. Let's consider the concept that quantum foam may be the very foundation of reality itself. If so, what does this mean for our understanding of time? The idea that time and space emerge from this quantum agitation leads us to question the nature of causality and the sequence of events. Could it be that before the laws of physics as we understand them existed, time was a completely different phenomenon shaped by this foam? As we delve into this sea of quantum bubbles, we encounter a universe that does not follow the rules of our day-to-day lives. Particles can appear and disappear, creating an environment where stability is merely an illusion. How can we reconcile this with our experience of time, which seems to flow so consistently and linearly? The answer may lie in how these quantum fluctuations integrate into what we consider macroscopic reality. One of the most surprising implications of quantum foam is that it could be responsible for the structure of space-time as we know it. Without these fluctuations, the universe might have remained in a state of chaos, unable to form the galaxies, stars, and planets we inhabit. So is it possible that quantum foam is not just a transient phenomenon, but an essential component of the universe's creation? In the realm of cosmology, quantum foam also leads us to rethink the notion of singularities. In the context of the Big Bang, where the universe originated from an infinitely dense point, quantum foam could have acted as a buffer, allowing space-time to emerge in a controlled manner. Could it be that instead of a chaotic explosion, the Big Bang was the result of a delicate balance of forces at the heart of quantum foam? The idea that the universe begins in a state of quantum chaos raises questions about the very nature of time. Is time an emergent property of quantum foam, or is it something that existed before the universe formed? The answers to these questions could change our understanding of what it means to exist in the cosmos. As we explore quantum foam, we also encounter the concept of feedback. Fluctuations at this smallest level can influence the large-scale structures we observe today. Thus, every star, every galaxy could be the result of a quantum dance that began billions of years ago. What other wonders might be hidden in this quantum fabric that defines our universe? However, the study of quantum foam is not without its challenges. As we venture into this territory, we face limitations in our tools and theories. Quantum physics, while powerful, has yet to fully unify our understandings of gravity and space-time. Are we close to discovering a new theory that explains how quantum foam relates to time and gravity? Ultimately, quantum foam invites us to contemplate a universe that is far more complex and beautiful than we can imagine. Each bubble of this foam could be a window into a new understanding of reality. As scientists continue to explore these ideas, a vast horizon of possibilities opens up. What else can we learn about the universe from these subtle fluctuations that, at their essence, might be shaping everything we know? The exploration of quantum foam is not just a quest for knowledge, but a journey to the heart of time itself. As we continue to unravel its mysteries, we may be on the threshold of a discovery that redefines our very existence within the vast cosmos. Are we ready to face the revelations that could arise from this journey through the depths of quantum reality? Before time began, what existed? This question has intrigued philosophers and scientists alike. The notion of before the Big Bang is fascinating and challenging. Most of us have grown up understanding that the Big Bang was the beginning of everything. But what if I told you that some theorists suggest there might be something before that monumental event? Imagine a universe without time, a vast void where there is nothing. But is it really possible that nothing existed? Some scientists argue that the concept of nothing is itself problematic. How can we define nothing? Is it simply the absence of matter and energy, or does it imply something deeper? In modern physics, nothing could be a state full of potential, where quantum fluctuations might have led to the creation of the universe. One of the most intriguing theories is the idea that the universe could have gone through cycles of expansion and contraction, known as the Big Bounce hypothesis. What if the Big Bang was not the true beginning, but rather the result of the collision of two previous universes? This concept not only challenges our understanding of time, but also raises the possibility that time may have never had a true beginning. But what about the dimensions of space and time before the Big Bang? Some physicists propose that time as we know it may not have existed at all. In this context, time could be an emergent property, something that arises from more fundamental interactions. If this is true, what would it mean for our perception of reality and our existence? Some researchers have speculated that before the Big Bang, there might have existed a state of energy vacuum where energy fluctuated. In this state, particles could have appeared and disappeared in a sea of possibilities. Could it be that the creation of the universe was simply the result of these fluctuations? An explosion of energy that gave rise to everything we know. Another theory suggests that time could be cyclical, implying that the universe expands and contracts in an endless cycle. In this model, each Big Bang could be followed by a big crunch, where the universe collapses back into a singular point. If this is true, are we living in an expanding phase of an infinite cycle? The idea of repeating time raises questions about the nature of existence itself. And of course, what role does gravity play in this scenario? Some experts suggest that gravity could have been the force that allowed the universe to emerge from this primordial state. However, if gravity was present before time, how can we understand its influence on the origin of time itself? This paradox leads us to question our understanding of the fundamental laws that govern the cosmos. Models of parallel universes also offer an intriguing perspective. What if, before the Big Bang, there were other universes that collided or merged, thus creating ours? This idea suggests that our universe is not the only one, but part of a constantly evolving multiverse, where each Big Bang could be the result of interactions between different realities. Quantum cosmology has also contributed innovative ideas about pre-Big Bang time. Some scientists argue that at microscopic scales, time may not be linear. In a quantum universe, there could be multiple states coexisting simultaneously, suggesting that time could be an illusion created by our perceptions. Could it be that before the Big Bang, time behaved in ways we do not yet understand? Furthermore, string theory offers another dimension to this discussion. According to this theory, the universe could be composed of tiny vibrating strings that generate the particles and forces we know. In this model, additional dimensions could exist before the Big Bang, suggesting that what we call time might just be a manifestation of these hidden dimensions. But how can we approach the question of causality in a context where time may not have existed? If there is no before in the traditional sense, how can we talk about causes and effects? This paradox raises profound questions about the nature of time and reality itself. On the other hand, what if time itself is an emergent phenomenon, something that arises from quantum interactions? This idea challenges our notion of absolute time and suggests that time could be a human construct, a way to organize experiences and events in our understanding of the universe. Reflecting on these theories, it is evident that the question of what existed before the Big Bang does not have a simple answer. Each theory opens up new possibilities but also generates more questions. Are we destined to live in uncertainty about the origin of time, or will we one day unravel the mysteries surrounding the beginning of the cosmos? Ultimately, the search for answers about what preceded the Big Bang leads us to explore the limits of our understanding. Science and philosophy must come together to address these fundamental questions about time and existence. As we continue to investigate, perhaps we will get a little closer to discovering the truth about the enigma of time and its origin. Is it possible that time has an end, just as it had a beginning? This question may seem perplexing, but it is one of the most intriguing reflections that scientists and philosophers have considered throughout history. Many wonder, what will happen to time when the universe reaches its peak and begins its inevitable decline? Some theories suggest that time could be linked to the expansion of the universe. If the universe continues to expand, could that mean that time also expands, or is there a limit to this expansion? The idea that time could have an end raises a series of fascinating questions. Could there be a moment when time ceases to exist as we know it? Most of us have grown up with the notion that time is a river flowing forward, inexorable and unstoppable. However, some physicists suggest that this river could run dry. What would happen then? Some theorists propose that time could come to a complete stop in the distant future, leading to a state where neither the past nor the future would have meaning. Let's imagine a universe that cools and expands indefinitely. In this scenario, stars would extinguish and matter would disperse. So what would remain? Perhaps an eternal void where time would no longer make sense. Without light, without life, how would we measure time in a world where there are no events to mark it? On the other hand, there is the hypothesis of the Big Freeze, where the universe expands so much that it eventually becomes a cold, dark place. Is it possible that in that state, time becomes an illusion without changes? Without movement, would time simply be a human construct, irrelevant in a calm universe? Some scientists suggest that even in an expanding universe, there could be disruptive events that alter the flow of time. Could these events be enough to restart time, giving it a new direction or a new beginning? In this context, time might not be linear, but could have cycles of creation and destruction. Now, if we consider the possibility that time has an end, what implications would we have to accept about our existence? The idea that everything we know could become irrelevant in a distant future can be daunting, but it can also be liberating. If time has an end, perhaps our daily concerns are not so significant in the grand scheme of the universe. However, the notion of an end to time raises another dilemma. What about causality? If time stops, does that mean that causes and effects also cease? In this scenario, could we say that time is an illusion created by our perception, or is it a fundamental constant of the universe that can simply change form? Einstein's theory of relativity tells us that time is relative and depends on the observer. So, if time can be different for different observers, could there be realities where time does not have an end but continues in ways we cannot imagine? With all these possibilities, a crucial question arises. Could there be a new type of time that emerges after the end of the time we know? Perhaps a time that is not linear but manifests in completely different ways than we currently understand. This opens the door to a series of even deeper questions about the nature of reality itself. Science continues to explore these concepts, challenging our beliefs about time and the universe. However, there is still so much we do not understand. Is it possible that in the future we will discover that time, as we conceive it, is just a part of a much broader and more complex phenomenon? Some scientists suggest that we might be on the path to a new understanding of time, where its end is not a point of hopelessness, but rather a new beginning. Perhaps time is just one of the many dimensions that we have yet to fully explore. The idea that time could have an end invites us to reflect on our own existence. We face the reality that everything we know, including our most cherished moments, is fleeting. But this also motivates us to appreciate every moment, every experience while we are still here. As we move into the future, we may continue to uncover surprising truths about time and its nature. The search for answers about the end of time leads us to question not only the universe, but also our place in it. So when thinking about time and its possible end, let us remember that the mystery of our existence and the universe we inhabit remains an exciting adventure, full of surprises and discoveries to come. What secrets does the future hold in our quest to understand time and its nature? Only time will tell. We have embarked on a fascinating journey through the mysteries surrounding the beginning of time and the universe. But what does all this really mean for us? As we reflect on these curiosities, questions arise that can change our perception of reality. Is time an absolute concept or merely an illusion? What implications does the existence of a time that may not have had a beginning hold? The low entropy paradox invites us to question the very logic of the universe. If everything tends to disorder, why did we start in such an ordered state? This is not only a scientific dilemma, but also a philosophical one. The search for answers leads us into a labyrinth of theories and hypotheses that challenge our understanding. So could it be that beneath this confusion lies an underlying order that we have yet to decipher? In our attempt to unravel quantum time, we realize that nature does not always behave predictably. If time in its early moments was discontinuous, what does this mean for our daily experience of time? Have we been living in an illusion of continuity? This perspective makes us reconsider not only time but also our own existence. As we delve deeper into quantum gravity, an intriguing question emerges. How did the laws of quantum mechanics and gravity come together to give rise to time? The answer to this question is essential, as it could provide us with clues about the very structure of the universe. But is it possible that there is more than one way to understand this relationship? Perhaps the key lies in accepting that there are things we still cannot measure or see. Cosmic inflation takes us to a moment of dizzying expansion that seems to defy all logic. How is it possible that in such a brief moment the universe could grow so much? If we consider that this happened in the blink of an eye, how can we even begin to comprehend the magnitude of what occurred? Perhaps the answer lies in accepting that our understanding is limited and that there are realities that surpass our imagination. Creation from nothing poses the greatest of mysteries. How could time arise if nothing existed before? This mystery goes beyond science and delves into the realm of philosophy. Is it possible that time itself is a creation of our consciousness, a way to organize experiences that would otherwise be chaotic? Perhaps we will never know for certain, but the quest for this truth is undoubtedly a fascinating journey. The arrow of time reminds us that time flows in one direction. But why is this so? What about the possibility of time loops or alternate realities where time does not behave this way? This concept invites us to imagine a much more complex universe where the rules we know do not apply. The zero moment is the great enigma. No one knows exactly what happened in that first moment. Could it have been a moment of pure possibility, where everything we know had yet to take shape? This idea leads us to think that perhaps the beginning of time was not a singular event, but a series of possibilities unfolding before our eyes. The initial singularity, that infinitely dense point where space and time would have originated, represents the limit of our knowledge. Is it really possible to understand something that is beyond our experiences and our logic? This question reminds us that although we have made significant progress, there are still vast territories to explore in our understanding of the universe. Hawking's imaginary time offers us a new way of thinking about primitive time. If time was curved and not linear, how can we apply this understanding to our current reality? The answer may lie in accepting that time is not a straight line, but a complex fabric of experiences and dimensions. dark energy, that mysterious force that seems to be accelerating the expansion of the universe, may have played a crucial role in the early moments of existence. What if this energy is the key to understanding not only the beginning of time but also its future? Speculation in this regard opens up a range of possibilities that invites us to continue exploring. The Horizon problem challenges our understanding of how the young universe synchronized. If there was not enough time for interactions to occur, how were the conditions established that led to the formation of structures? This question serves as a reminder that often the answers we seek are hidden in the subtlest details. Theories about parallel universes lead us to even more intriguing thoughts. If other universes exist with different flows of time, what implications would that have for our own existence? Could it be that our experiences are just a fraction of what is really happening in the vast multiverse? The Big Bounce hypothesis suggests that time may not have begun but rather restarted after a previous collapse. This presents a cyclical view of time that could change our perspective on the past, present, and future. Is it possible that we are trapped in an endless cycle of creation and destruction? Perhaps the answer to this question will help us find a deeper meaning in our lives. The dilemma of causality is another fascinating aspect of the beginning of time. If time was born in the Big Bang, how could there have been causes for that beginning? This enigma reminds us that as we attempt to unravel the secrets of the universe, we often find ourselves with more questions than answers, and this perhaps is what makes the pursuit of knowledge so captivating. Finally, Einstein's relativity offers us a unique perspective on how time depends on space, but still leaves us in the dark about its origin. What does this tell us about our daily experience of time? It is a reminder that time, although we perceive it as linear and constant, is actually a construct that can be shaped by the forces of the universe. As we conclude this journey through the mysteries of the beginning of time, it becomes clear that our questions are as important as the answers. Each enigma we have explored invites us to continue inquiring, to keep questioning. Perhaps we will never fully understand time and its origin, but in our search we find not only answers, but also a deeper connection with the universe we inhabit. Curiosity is, after all, what drives us to move forward, exploring the unknown and embracing the wonder of what is yet to be discovered.